Hello and welcome to lesson 23 of this Introduction to Probability of Wolfram. The topic for this lesson is the law of large numbers. Let's begin. So far, this course has an increasing complexity, going from simple experiments to complex multivariate distributions. The most important distributions, like the binomial and the normal, have CDFs that are impossible to compute exactly. But what does that imply? How do you compute it then? In a word, asymptotics. Asymptotics is the calculus of approximations. It's used to solve hard problems that cannot be solved exactly and provide simple forms for complicated results. In probability, these approximations often relate to the sample size n. You'll learn about asymptotics, the Markov and Chebyshev inequalities, and the law of large numbers. So first, practically, what does it look like? Asymptotics aim to approximate complex calculus using polynomials, which are easy computationally. The asymptotic probability function is similar to the probability function, with the difference that there is an initial point and the degree of the polynomial used. So, what's the asymptotic probability that x is greater than a, where x is a standard normal and a tends to 1? Take the asymptotic probability x is greater than a, x normally distributed, and a around 1, let's say with 2 degrees. And here's the approximation. As another example, use the asymptotic probability for e power x power 2 minus x minus 1, where x is exponentially distributed around 1 with 3 degrees. If you calculate this close to 1, let's say 1.06, you'll get an approximation of the corresponding exact numerical probability, with some slight error. These are preliminary notions necessary to understand the important theorems of this course. So first, Markov's inequality may be stated as follows. Let x be a random variable. Then for any non-negative value a, the probability x is greater or equal to a is less than or equal to the mean of x divided by a. This is true for any probability distribution. For example, the normal distribution, where the probability on the left is always lower than the mean divided by a on the right. Next, Chebyshev's inequality may be stated as follows. Consider x is a random variable with mean mu, variance sigma squared, and k greater than 0. Then the probability the difference from mean is greater than k is less than or equal to the variance divided by k squared. This is just a consequence of Markov's inequality. Since you can just take the formula, replace y by the squared difference from the mean, and a by k squared. Then simplify the square on the left, and replace by sigma by a definition of the variance. And here's the interpretation. At least this percentage of the distribution is at most k standard deviations away from the mean. So this is a form of lower bound. Okay, now for the main theorem. The weak law of large numbers can be stated as the sequence of n independent, identically distributed random variables, each having a finite mean mu, where the probability of the average of the sequence value minus the mean greater than or equal to epsilon tends to zero as the sequence grows. This theorem can be directly derived from Chebyshev's inequality by replacing x by the average of the sequence and realizing that the probability is between 0 and a reducing number, meaning as n grows, the probability tends to 0. That's a lot of notation though, so let's approach it intuitively. The weak law of large numbers is essentially this. As the number of trials of a random process increase, the difference between the true expectation and the mean of the sequence gets smaller and smaller. In fact, this can be formulated in many ways depending on your field. In statistics, we say as the sample size grows, its mean gets closer and closer to the population mean. In finance, it implies the larger the entity, the slower the growth tends to be. In insurance, as the pool of clients grows, the risk of loss is reduced, which fundamentally motivates pooling. To simulate the weak law of large numbers, consider you're 40% likely to win a game, and you can play as many games as you want. If you leave after n games, what's the probability you make a net positive? So at least half of the games are won. Take the probability that x more than n divided by 2 for a binomial of 0.4, and as you can see, the probability gets lower and lower as the number of games increases. This phenomenon of the uncertainty dropping as the sample size increases is everywhere. But as you can guess, that weak law also has a stronger version. That is, for a sequence of independent random variables of different means, the difference between distributions and their means is reduced to epsilon, which is as close to 0 as desired as n grows. Unlike the weak law of large numbers, this law doesn't require identical random variables. In fact, as long as the number of trials of any random process increases, the difference between population and sample mean will be reduced until it becomes insignificant. Consider a large number of experiments of unknown distributions with an average expectation p of success. Then the empirical mean of these experiments is approximatively p. This idea is expressed in this example, which shows the movement of the average as the number of samples increases. So, as a summary, asymptotic probability tools aim to estimate calculus with polynomial formulas, which is more efficient. The Markov and Chebyshev inequalities lead to the law of large numbers, including both the weak and the strong laws. These theorems have notable consequences for the binomial and normal distributions, as seen in the next lesson.